2D. 3D, we leave it for the next time. Yes.
So it's not going to cover the material that's on our homework that'll be due.
That's 3D, right?
That's 3D.
Yeah, 3D, no.
Okay.
And then equivalent systems. And moment about an axis. And you know me by now, right? You will have 5 or 6 bonus points. And you have to study what for that? Wikipedia's.
Jeopardy.
Okay. 2 on current events and 2 on 1 U.S. history and 1 on world geography, something like that. So that's a big hint, isn't it? Yes.
So, do we need to do free body diagrams for everything? Because that was unfair.
I will specifically state that, right?
Okay.
Oh, okay, cool.
Yes. Okay. So let's continue equilibrium of rigid bodies, right? So rigid body equilibrium. I will do one more 2D problem, and then I will start the 3D equilibrium. Yes.
Kind of like about the exam. Will you send us like the I forgot what.
Those sample problems?
Yeah, the sample
Yes,
problems,
in
like
fact,
review sample
there
problems.
are a couple of things that I'm going to do today. Send you that. I need to send you, of course, a solution to the last homework, the one that you turned in. And also the last 2, I guess, or 3 videos, I haven't uploaded them, so I'm going to do that too.
Okay.
I'm going to do all of them tonight.
Such a busy man. Such a busy man.
So let's do a problem. This is an example that I want to do. Let's say you have a structure that is like this, and you have three pulleys that are attached to this structure. And so you have here, connection here and here. And so let's give you these distances that you need. So let's say this is 2 meters, 2 meters, and this is, say, 1 meter. This distance is 3 meters. And you have a cable that is holding a 30 Newton weight here, goes around this pulley, wraps around this one, goes here, comes down, and it is attached to the ground, okay? And you want to find, so you basically find all unknown reaction or support forces. Intentionally, I will do this problem in 2 different ways. There's an easier way, there's a more extended or extensive way of doing it. I do it the long way. The reason for that is I want to sort of pave the road for a topic that we'll discuss later. Nevertheless, it is related to rigid body equilibrium. So when I'm asking you to find the all unknown reaction forces that are holding the structure together, let's remember or think of that this is the structure that we are interested in. That's the structure we want. First of all, step 1 is easy, right? And step 1 is set up X and Y coordinates. So this is X, step 1. But for step 2, which is setting up the free body diagram, let's say this is the structure. I'm going to get rid of everything else that is connected to it, just focus on that structure. So I'm interested in finding what are the supports here. Obviously, this is a fixed support, So I have a force, let's say if I label this as E, I have a force at I call it dy, dx. There's also a moment that is resisting the rotation at that point, right? So if I get rid of all those pulleys, let's see what is the consequence. See, look at pulley 1, or pulley at A. This pulley is subjected to a force due to this cable that goes around this, of course, 30 Newton and 30 Newton. The pulley is connected to the structure through this pin at A, right? And that means a force AX and AY that come from the structure acting on this pulley are holding it in place, right? So what that means then is law of action and reaction, third law of Newton. If these forces are supporting this pulley coming from the structure, on this structure, at point A, we have two forces equal in magnitude and opposite in direction, right? Is that clear? Okay. Of course, it's not difficult to find these forces because I can actually, if I connect these two, right? If let's say the radius of all of these pulleys are 0.5 meter, I can actually find this angle alpha. This is 0.5, this is 1 meter. So in this triangle, tangent of alpha is 0.5 over 1. That gives me alpha to be almost 27 degrees. Okay, so I can find then AX and AY from this free body diagram for this pulley. Or I resolve this into its components. That is, if this is alpha, this is 30 cosine of 27. This is the 30 sine 27. So I write equations of equilibrium. Sum of forces along x is equal to 0. I have negative AX plus 30 cosine 27 equal to 0. That means AX is 30 cosine 27, and cosine 27 is about 20, I think it should be about 28 or 29. You know, check that, please. But it came out to be positive.
26.7.
26.7? Sorry, we're way off. So it would be 27. So it came out to be positive. That means the assumed direction is correct. So this is 27 Newton then. Okay? Summation of forces along Y being 0. I have negative 30 Newton. Negative 30 sine of 27. This one. Plus y is equal to 0, or ay would be 30 times 1 plus sine 27. So that would be about 44 maybe. Sine of 27 is almost 44.
43.6.
Okay, so 44. So again, came out to be positive, so that means this is the direction, the assumed direction is correct. So that means the result of removing that pulley means that there are two forces acting on the structure. Yes?
I'm confused why in the smaller drawing, AX and AY are in the opposite direction where you put them on the bigger drawing.
Or you mean why from here to here, this becomes the opposite direction to these?
Yeah.
Right. See, as I said, when these two pieces are connected together, pulley is connected to the structure. If you take the pulley apart, at that point A, or the pin, forces that are acting on this pulley to hold it in place are coming from the structure, right?
Okay.
You remember the third law? When two bodies are in contact, right, they exert a force equal in magnitude and opposite in direction on each other at the point of contact.
Okay.
So at the point of contact A, pulley is exerting a force on this body which is opposite to these. Okay, any other questions? So B would be the same. So this is 1, let's say 2. Let's consider the free body diagram of that pulley at B. So this is the pulley at B. I have this force, let's say By. I have, let's say Bx, maybe in that direction. And then I have this 30 Newton force here and 30 Newton force here, and both of these are alpha. Okay. So if I can immediately see that the assumed direction is wrong here. So I better fix that. It should be this way. Right? So obviously summation of forces along y is 0, will give me negative By plus 2 times 30 cosine of 27. So By would be 60 times cosine. Yes.
Why is it cosine?
Oh, I'm sorry, sine of 27, right. That would be sine of 27. So it would be almost 30, or less than that, yes.
Should the arrow for AY be pointing the other direction?
Here,
No, on the free body diagram.
so if this is going that way, on this one should be downward, right? These are forces, as I said, coming from the structure, acting on the pulley. So whatever these forces are, acting on the pulley, you have forces equal in magnitude, opposite in direction, acting on the
Yes.
structure.
But since both cables are pointing down, downward should have been.
This should be up. This is correct, right? But if this is a force from the structure acting on the pulley is exerting a force in the opposite direction of the
Okay,
structure.
I got it.
Right. So on the structure, it would be the opposite. Any other questions? So how much would that be? That would be about 30? 27.23. So 27 then. So 27 Newton, direction is right. So if this is downward here, I have a force of By equal to 27 here, right? If you write summation of forces along X equal to 0, just happens that you see that Bx, you have minus 30 cosine of 27, right? Plus 30 cosine 27 equal to 0, so Bx would be 0. Okay? So no X force here. How about at point C? Let's do that free body diagram. For this pulley at point C, I have a force of 30, right? And this is alpha, or 27. Then I have a force of 30, like this. So at point C, I say I have a Cy, and then I have a Cx, like this. So again, writing summation of forces along X equal to 0 this time, I have Cx minus 30 cosine of 27 equal to 0. So would be, we had that here before, right? So that would be also, Cx would be also 27 Newton. And the direction would be correct. So you have a force of, if this is acting that way, you have a force of 27 Newton acting on the structure this way at point C. This is B, this is C. Okay, and this is, you have this, oops, and this, 2 meters, 2 meters. I should have moved this a little bit that way. Doesn't look good. So let's move this way. Okay, that's better. Okay, and this is 1. So summation of forces along y is equal to 0. I have negative 30 sine 27, negative 30 plus cy is equal to 0. So cy is 30 times 1 plus sine 27. How much? 44.
Same as you.
Oh, okay. So again, the assumed direction is correct then. So I have a force of 44 Newton like this. So that would be the free body diagram. Yes.
So because A and C have the same geometry, could we just say that they're going to be the same forces?
You could say that, good point. They are basically, they have, the forces acting on them have the same geometry. Yes. You didn't have to solve for those. Good point. Good point. Yes. Any other? Yes.
When you're picking the assumed directions for X and Y, is there like an easy way to tell like if your like assumed direction is going to be right or wrong? Or
I mean,
just have to
frankly,
guess?
the easiest way is just assume anything you want. If it
And then
comes
just
out to be
figure it out.
negative, that's
Just
easy.
switch it.
There's no like trick to like.
No, sometimes it's easy to visualize. For instance, here, you can see that if you look at summation of force along X, since you have only one force going this way, CX has to be this way. So before doing it, I just assumed
Gotcha.
that to be the correct direction.
Okay.
And same thing with Y. Both forces, known forces downward to the unknown. But you don't have to.
Okay.
You don't have to know ahead of time. Any other questions? So now you have the complete free body diagram of this structure, and you want to find the support force at point C. So you just write summation of moments at C is equal to 0, assuming this is the correct direction. So you have, I'm sorry, D.
Okay, yeah.
D. So MD is in the negative direction. These two don't make any moment at point D. These, like, look at these forces first. This makes a clockwise moment. This is the distance given. So you have negative 27, moment arm is 3 meters. This one makes a counterclockwise moment, same moment arm. So we have plus 27 times 3 meters, which apparently cancel out. Then at BY, what happened to BY was that way, right? This is BY. So that's 27 going also clockwise. So you have negative 27 times this distance, which is 3, happen to be the same. Then this one going counterclockwise again, so you have plus 44 times 1, and then you have, I forgot about AY. Also AY makes same counterclockwise moment. The moment arm is 5, so you have plus 44 times 5 is equal to 0. So 44 times 6, minus these two cancel out, right? If you could give me that, I'd appreciate it. That's gonna come out to be negative, I think. Empty.
44 times 6 minus 27 times 3. is
Right.
180.
183 negative or positive?
Unless I change the
Oh, that's right, yeah, this is positive. So that means they assumed the erection, what we have assumed, is correct. So this moment is acting in this direction. Yes.
I know the, like, the reaction of the support moment to be in opposite directions, but how did you know that?
This one?
Yeah, did you just? for
No, I
the
just
MD,
assumed that.
You just.
I just assumed it, right.
There's-
And apparently it came out to be positive, that means the assumed direction is correct.
Okay.
Yeah, you
So
don't have to know.
you're indicating the direction there just because you know it's gonna be opposite, but you don't
Correct.
really know, okay.
Yes, exactly. Any other questions? So, summation of forces now along x is equal to 0. So you just have negative 27, positive ax, which is plus 27. And those are the only forces you have along x, plus dx is equal to 0. So dx just happened to become 0 because of the way the numbers play. Okay? And then summation of forces along y is equal to 0. So you have 44 downward at C, so negative 44 Newton. You have 27 upward at B, so plus 27 Newton. 44 downward at A, so minus 44. And those are all the forces along Y, plus dy is equal to 0. So we have negative 88 plus 27. How much would that be? 61. 61 positive. So the assumed direction is correct. And that's it. So this is the way I did it. I assumed that I wanted to consider only the free body diagram of the structure. There is actually an easier way to do this problem, but I intentionally did it this way for a reason. As I said later, you will, when we get to frames, we have to take all members apart. So this was kind of a, in a way, paving the road towards the topic that we'll cover later. Because, as I said, the objective of this problem is, the problem is asking find all unknown reaction or the support forces. How is this structured? Yes?
So you know, I guess as implication for what we're doing later, what's the easier way of doing it?
I'm going to do that right now.
Okay,
Sure.
there we go.
See, no problem. If I let me ask you this question. I'm asking that what are the support forces, right? So how is this, if you consider pulleys as part of the structure, not taking them apart, what do? You only cut the structure at the supports, right? So all you have to do then, just cut the structure here and here, right? So you will have that MD, that dy, and dx, and then you have this 20 Newton here, oh, sorry, 30, and 30 Newton here. But you don't cut anything inside the structure because you're looking at this as the structure as a whole, meaning that the pulley, the cable, everything within the structure is intact because it's a part of the structure. You only cut the structure from its supports. If you look at it this way, right, you can actually easily see that. You write summation of moments about this, you can easily find the force at the moment MD. Summation of forces along Y immediately gives this to you, which is going to come out 60. Yeah, we were close, about 61 due to that angle alpha. That should be also 60. And summation of forces along X is actually 0, so dx is going to come out to be 0. So this is by far the easier approach. As I said, the only reason I took them apart, I wanted to show you what is the difference between the free body diagram of this structure. If I consider that as my structure, you have to basically take everything that is attached to it away from it. put the effect of that back on the structure in form of these forces. But other than that, if you just want to find the supports, this is the easiest way. Okay? So this was a different type of problem, just to at least give you a heads up for future. But in summary, as far as rigid body of equilibrium of 2D objects are concerned, simple, right? Just cut the support, put back the effect of the support, which basically means either a one unknown force, two unknown, or two unknown forces and a moment. That's it. And apply equations of equilibrium. That's it. That is it. Very simple. Any questions? No. So let's move on to the next topic, which is rigid body equilibrium of 3D structures.
You said this won't be on the exam.
No, this, no, the two Ds would be, 3Ds would be.
Yeah.
Yes, 3Ds, no.
Also, there weren't any two-force members on our homework. Should we expect two-force members on the exam?
I did go over two force members, right?
Yeah, there were some on our homework.
Right.
At least one.
I think there was
So
one.
we discussed
This
two
week.
force members.
Okay.
So, two force members are good. As I said, three things that you will never forget, right? What were those three things?
Saint Varagon, two force
Saint
members.
Varignon. Free body
Venn
diagram.
and two force members.
Two force members. Okay. Somebody actually in the other class came to me. He wanted to do a good research on Mr. Saint Varignon. Believe it or not. So he wanted to learn more about his life history. So I'm going to be curious what he has learned. Okay. All right. So we're going to discuss now 3D equilibrium. 3D rigid body equilibrium. Rigid body equilibrium is not much different from 2D. The only difference is this. In 2D, when we talk about support mechanisms, we have only three possibilities for how those mechanisms would prevent motion. They either allow motion in only one direction, right? Two direction, or three directions, right? That's it. So if rotation and translational motion is allowed and one direction is prevented, that was a roller. If rotation is allowed, two translational or not is a pin. And if nothing is allowed, we have three unknowns, two forces and a moment, right? In 3D, the mechanisms are not as simple as a 2D case. They can be, but at least the physical configuration is not as simple as we can sort of directly identify or categorize these. There's a good table in your book that I strongly recommend you to look at it. If you open the book, on the first page, right on the back of the front page, there's a table for 2D support, and then right next to that page is a table for 3D supports. That table, I guess, is table 4.10 in chapter 10 also. But concept is the same. You may have, for instance, a support that allows rotation in all directions. We call that rock and pinion joint, for instance. Okay? Or a socket joint that allows rotation but does not allow motion in any direction. You may have a bearing, a journal bearing, or all kinds of other bearings that allow rotation in certain directions and translational motion in some directions, but they don't allow some motions. Generally, when you're given a problem in 3D, you are given enough information to figure out what motions are prevented, so you know what your unknowns are, or explicitly, that information is given to you, okay? But with that said, as far as the steps are concerned, step 1 in 3D actually is easy, because you're always provided the coordinate systems. You don't have to set it up. Step 2 is the same. You need to set up the free body diagram. You can imagine in 2D you had no maximum of 3 unknowns, right? In 3D, if the motion is prevented in all 6 directions, so the maximum number of unknowns then is 6, okay? But nevertheless, the setting up the free body diagram is the same. You cut the structure from its support, put back the effective supports. So you can have anywhere from 3 to 6 unknowns at each point of connection. And then, as far as the step 3, which is equations of equilibrium, in 2D, you have summation of forces along x0, summation of forces along y0, and summation of moment about any point is 0, where here you consider summation of moments about point of intersection of 2 unknowns, right? In 3D, you will, of course, have summation of forces along z direction is also 0. And the equivalent of this is this. At least that's what I prefer. Since you have so many unknowns, it is most of the time possible to identify an axis that intersects through, say, 4 or 5 unknowns. So if you can find that axis and take summation of moment about that axis, you can eliminate more than 3 unknowns. And you end up with only 1 or maybe 2 unknowns. So analogous of this in 3D is summation of moments about an axis which intersects with as many unknowns as possible. If you don't want that, you can just write summation of moments of all forces about x, summation of all forces about y, summation of all forces about z equal to 0. So you have 6 equations, 6 unknowns, you can solve for all of them. So let's demonstrate that through an example, and we'll do more on Wednesdays. The only thing with 3D's, case of 3D, is that it's just more involved in terms of the algebraic equations that you need to derive. It's more time consuming. The concept is simple. It's just more time consuming. Let's look at this problem, which, if I remember it right, is from your book, or at least some version of that is from your book. And I find it as a good example to begin with. So here you have a pole. At point A, it is supported by a pin that allows motion in all 3 directions. Motions along x, y, and z are not allowed. Then there's a cable attached to this, parallel to the x-axis, that carries 100 Newton force. Or in other words, there's a cable that is holding this structure that way. And then at this point B, let's say, if I call it C, B, so let's say C is 10 meters here, B is in the middle, so 5 meters. B is connected over to 2 cables that connect this to the ground at, maybe make it a little bit more interesting. Maybe these cables go like this, okay? So A, B, C, D, E, okay? So let's say, I just make it easy. So coordinates of this are given maybe as 2, 0, and negative 1. Coordinates of this are given as 1, 0, and 4. C obviously is given as 0, 10, 0. B is given as 0, 5, 0. And this is 0, 0, 0. So you want to find reaction forces at A and forces in cables BD and CE. So in other words, what you've been asked is to find all the support reaction forces, everything that is holding the structure in place, which are these cables, this support, that support also is a support, but the force in that is given. So you know that already, okay? Procedure is as follows, okay? I will try at least, step 1 is, as I said, is given. You already have these coordinate system. For step 2, you draw the free body diagram to make life easier. I'm going to do that on this here. So the motion in these X, Y, Z are not allowed. So I assume there's a force on AY here, there's a force on AX here, force on AZ here. Direction doesn't matter. Like before, it may come out to be negative, and that means the assumed direction is wrong. So I cut this cable, so there's a force of BE here, and there's a force of BD, and obviously I have this force of 100 Newton. So that is a free body diagram, okay? So those 2 steps, relatively straightforward. Step 3 is what really is the time-consuming part. But again, like before, I always encourage you to start with summation of moments. It's your choice. You can either start with these 3 equations, or an easier way is to find an axis that intersect through as many unknowns that you want to get rid of, and only find one unknown first, and then use the other equation to find the rest of the unknowns. And that's what I would do. Is there a possibility that I can find an axis that intersect through, I have 4 unknowns, 5 unknowns, right? Can you find me an axis that cuts through 4 of these unknowns, so it leaves me with only 1 unknown to find? Can you see that? Anybody? Yes?
You go through the origin in one of the 2 points of the force.
You said it. Yes. If you look at this axis, for instance, if I take summation of moments about AD equal to 0, right? This force and these 3 forces intersect with that axis, so I only end up with this and that force. That force is given, so I only have 1 unknown. But look what this involves. You need to take moment of force BE about this axis AD, which will be a number, plus the moment of that force 100 Newton about AD, equate this to 0, that will give you the magnitude of the force BE, okay? But how? Now we have to dissect each one of these, because each one of those involves several steps. As long as you do it methodically, step by step, you don't make any mistake. What is the meaning of the moment of FBE about axis AD? You remember, moment about an axis means moment of this force BE about any point along this axis, right? Dot product of that and the unit vector of that axis. So moment of that force about A requires that I introduce a position vector connecting this to any point along this force. What position vector do you recommend? What is the easiest? You can connect this to here or here. Which one is easier? AB. So I will write this as AB cross that force BE, right? AB is only what? 5J, right? But how about this? I need to write the vector equation for that force, which means the magnitude of the force BE times the unit vector along BE. Coordinates of these 2 points are given, so it would be 1 minus 0, or I, 0 minus 5 minus 5J, 4 minus 0, 4K, divided by 1 plus 25 plus 16 square root, right? So you set that up. How much would be this? I have 41, 42. Square root of 42.
6.48.
6.5, how about that? So would you be kind enough to give me 1 over 6.5, in other words, simplifying this?
0.15,
Okay, 0.15,
negative 7.69.
7 point, oh,
7.77.
0.769? 0.69 you said?
0.769.
How about 0.77?
Yeah. And then 0.62.
0.62, okay. So, how do you set this up? So you need to set up this determinant, I, J, K, right? 0, 5, 0. Then you have f of BE here, right? Then you have 0.15, negative 0.77, and 0.62. That's this moment, right? So this will result in something like this. F of BE, right, times, for I would be 5 times 0.62 minus that. So it would be about 0.3 I. For J would be 0. For K would be minus 0.25. No, I'm sorry, 0.75. So minus 0.75 K. So this is equation for this. You need to find dot product of that and this unit vector, right? So now you need to set up this unit vector, find the dot product, right? You do exactly the same procedure for this one. Add them up, equate them to 0, you will get the first unknown that you're looking for. So that's what I said, that 3D is just cumbersome. It's tedious, long work, but it's not difficult, as long as you remember the concept, okay? See you on Wednesday, I'll do more problems.
What does Liz say?